Imagine hanging a weight from a spring. As the load increases, the spring stretches. Double the load and the extension doubles. Triple the load and the extension triples. This predictable relationship is not a coincidence. It is described by Hooke's law, one of the most fundamental principles in engineering mechanics. The law explains how force and deformation are related and forms the basis for understanding springs, structures, machine components, and even finite element analysis. Hooke's law states that within the elastic range, the restoring force developed in a spring is directly proportional to its displacement from equilibrium. Mathematically, F equals minus k times x, where k is the spring constant and x is the displacement. The negative sign indicates that the restoring force acts opposite to the direction of deformation. This simple equation allows engineers to predict how much a spring will deform under a given load. The spring constant, k, represents stiffness. A spring with a low value of k is soft and deforms significantly under load. A spring with a high value of k is stiff and resists deformation. For the same applied force, a softer spring stretches more while a stiffer spring stretches less. Engineers use the spring constant to select springs for vehicle suspensions, industrial machinery, vibration isolation systems, and many other applications where controlled deformation is required. The same concept behind Hooke's law applies to engineering materials. For a spring, force is proportional to displacement. For materials, stress is proportional to strain. This relationship is expressed as stress equals Young's modulus multiplied by strain. Young's modulus represents material stiffness and is the material equivalent of the spring constant. The higher the modulus, the more resistant the material is to deformation. This principle forms the foundation of mechanics of materials. Hooke's law is valid only within the elastic region of a material. In this region, stress and strain are directly proportional, and the material returns to its original shape when the load is removed. Once the yield point is exceeded, permanent deformation begins. The stress-strain relationship becomes nonlinear, and Hooke's law no longer applies. Understanding this limitation is essential because most engineering calculations assume linear elastic material behavior. Hooke's law appears in countless engineering applications. Vehicle suspension springs absorb road irregularities by deforming elastically. Load cells measure force through small elastic deformations. Bolts behave like springs when tightened and create clamping force through elastic stretching. Most linear static finite element analyses also assume Hooke's law by using stress proportional to strain. Let's summarize. Hooke's law tells us that force is proportional to displacement, while in engineering materials, stress is proportional to strain. The constants K and Young's modulus represent stiffness in springs and materials respectively. Hooke's law is valid only within the elastic region, where deformation is fully recoverable. This simple relationship forms the foundation of machine design, structural analysis, material mechanics, and finite element analysis, making it one of engineering's most important principles.